Hello and welcome to a short video where we're going to run through a linear dynamic analysis on the wind turbine model. What we're going to do is effectively apply a forced vibration by applying a harmonically varying force to the top of the nacelle here, top of the turbine, and we're going to measure the response of the system over a range of different frequencies. So what we'll do is we'll measure maybe the displacement of the top of the tower at a range of different frequencies and measure the stress at the bottom of the tower and plot out graphs of the response of the system. Now we could just use some of the simulation nodes to track that movement, for example. I'm going to show you another way of doing that. We could apply what's called a sensor to the model. So effectively we set up a predefined location that we can track either the movement or the stress or whatever quantity we're interested in. It's sort of an optional step, I suppose, but in certain models it can be quite useful to have a predefined sensor or predefined node, if you like, that you can track information on. Now in order to do that we need to have some geometry to track. We could pick an edge or a face or something. But what I'm going to do is I'm going to go in and edit my nacelle part, and I'm going to create a point in space that we can set up a sensor on. Okay, so I've gone in to edit the nacelle part. Within that, then I can go to reference geometry, create a point, for example, at the center of this nacelle face here. So that has just created a little point here, and I'm finished editing that part. Okay, so back in my assembly, I can go up to sensors here, add a new sensor, and I could track things like simulation data or mass properties or measurements and so on. In this case we want to track simulation data. We could specifically track stress or displacement or whatever. I'm going to set up what's called a workflow sensitive sensor, so I can track various different quantities depending on what we're doing. Okay, and in the blue box here then I want to select that point that I created earlier. Okay, so we should now have a workflow sensitive sensor, and you'll see later on then I can, when I'm looking at my response graphs and so on, I can just select that point in the center of this face. Okay, so with that little bit done, I'm going to go ahead and create a new study here. So we'll go Simulation tab and create a new study. The type of study that we're doing is under Advanced Simulation. You'll see Linear Dynamic here. And there's various different types of linear dynamic studies. Modal time history kind of plots maybe amplitude versus time or something like that. Harmonic here is the one we're looking for. It's going to apply a harmonically varying force or a sinusoidally varying force to the model at a range of different frequencies. Okay. Now, maybe the first thing we'll do is we'll have a look at the study properties. So if we right click in here, go down to study properties, what we can do is to select how many different natural frequencies of the tower we want to simulate. Similar to the frequency study that we looked at previously, or we've already run a frequency analysis where we looked at the first 10 natural frequencies, but because there are multiples, so if you recall from the frequency analysis, there's 2 duplicates of each one of the first 5 natural frequencies. So if I set this to 10 here, effectively I'm looking at the first 5 modes of vibration of the beam. And that's all I want there. If I go over to harmonic options, then this is looking at the harmonically applied force that we're going to be applying to or rather harmonically varying force we're going to be applying to the tower. You can set the units to radians per second or cycles per second. I'm going to set the lower limit to 0 and I'll set the upper limit to 100 Hertz. So I think our 10th natural frequency was something like 90 Hertz or something like that. Okay. Under advanced options then, I'm going to go in and change this, the number of points for each frequency. So effectively the way the simulation works is it'll run multiple different studies, multiple different simulations at a whole range of different data points along the frequency response of the system. So if we have 10 natural frequencies and we set it to do 15 studies or 15 data points for each frequency, that would be 150 different studies, which might take quite a while to run. So I'm going to reduce that figure a little bit to, let's say, 8 points per frequency. So we should have approximately 80 studies in total. It'll be a little bit more than that, but that kind of ballpark. Okay. Now, if I was to set this study to run as is, with both of these parts being treated as solid bodies and meshed with tetrahedral elements, I'd be effectively running 80 different studies with tens of thousands of nodes. I might do that as a demonstration, but that would take quite a while to run and would wind up with, using a large amount of system resources, and with large amounts of, it would take a long time to run. You'd have large data results files. So what I'm going to do as maybe a first approximation is I'm going to treat the tower part here as a beam. So when we create a mesh, I'll do that now. When we create a mesh, it'll mesh this one using beam elements. So the tower itself will be meshed using beam elements, whereas the nacelle will be meshed using the solid tetrahedral elements. Okay. Now this is what's known as a mixed mesh, where one part of the model is in solid elements, another part is in beam elements or shell elements or something like that. So it can be tricky to get these to run correctly, but in this case it should be relatively straightforward. The system has automatically created joint groups for us, and it's automatically created a global bonded connection between the two bodies here, the beam element, or the tower, which is meshed as a beam, and the bottom face of the nacelle here, which is solid elements. Okay, so the next thing I want to do is to apply my fixtures, and what I'm just going to do is apply a fixed geometry fixture to the joint at the bottom of the tower here. So I can either apply my fixtures to faces and edges, for example the bottom edges of the tower here, or I can apply them to the joint itself here. So I'm going to fix the joint at the bottom so there's no movement and also no rotations. This fixed geometry option. Okay. I might look at damping first, and then we'll talk about the loads afterwards. So if you apply a force to, if you have an undamped system and you apply a force to it, in theory you could get an infinite resonance, so infinite amplitude. In the case of Solidworks here, it just won't run the study. It'll come up with excessive displacements in the simulation. So you have to set up some amount of damping. I think we specified in the brief for the assignment, we specified damping ratio zeta equal to 0.05. So I'll just expand this out a little bit. You'll see here it's going to apply modal damping, and for the first 10 modes, which is what we've specified, we need to specify zeta here. So 0.05. Okay, so we have our parts here. We have materials applied, we have a bonded connection between the two parts, we have a fixture at the bottom, we have a mesh, and we have modal damping set up. The last thing we need to talk about is the loads. So I'm going to apply a force to the top of the nacelle, or to this circular face of the nacelle, so that my force is running in the X direction. And we're going to set up the force applied to that face, and applied with an amplitude of 100 newtons, normal to that face. Now, what this value here is, this is the amplitude of a harmonically varying force. Solidworks is not explicit about that, but effectively that's what we're doing here. So you can set up the amplitude of the force or the magnitude of the force, but effectively what it'll be doing is it'll be applying plus or minus 100 newtons to that, forward and back in the X direction, as a sinusoidally varying force. We could, for example, if it was a centrifugal force or something like that, we could set it up so that the amplitude increases with the frequency. If we set this as constant here, you'll have a constant amplitude sinusoidally varying force, which is what we want in this case. Okay, and that is the study set up and ready to go. When I click run here, it's going to run through a certain number of studies, one after the other. It'll be something in the region of 80, maybe a little bit more than 80. So I may pause the recording as that runs, but we'll start it off and see what it looks like. Okay, let's see here. See here, it's set to run 89 steps in total. So I'm going to pause the recording for a couple of minutes here as that runs through. Because we're using beam elements, it's running fairly quickly through these. If we had solid elements, it might take quite a while longer to run. Okay, and I'm back. Now that took me about 5 minutes to run that simulation, I'd say, about 2 or 3 minutes for the strain calculations, and then it had to run through all 89 simulations again for the to work out stress calculations. So what the simulation has effectively done is it's run through 89 separate simulations. You can look through those plot steps individually. You're looking kind of at 89 different sets of graphs here. Looking at in this case, looking at the stress. And this is looking at von Mises stress in the nacelle, which is not really what we're interested in. So you could set up different results plots if you were interested, say, at the, let's say we want to find a stress plot for the beam elements, for example. So this would be the stress in the tower for plot step number 89 or plot step 1. So if you're applying, what plot step 1 here is applying our harmonic force of 100 newtons at a very, very low frequency, effectively just over 0 hertz. So very, very slowly applying plus or minus 100 newtons, you would get something like 10 megapascals of stress down at the very bottom. So 1 by 10 to the 7 pascals. So that's for plot step number 1, applying the force very, very slowly. Plot step number 2 is applying it at 0.07 hertz, at 0.15 hertz, 0.25 hertz roughly. And our first natural frequency, I think, was something like 1 point something hertz, wasn't it? 1.14 hertz or something like that. So you can see at that frequency, at 1.5 hertz, we're getting something like 63 megapascals. Okay, so you can kind of individually look at the different plot steps. On their own, they're not especially useful, all those individual plot steps. They're useful enough, but it's much more useful to be able to get a graph of all of those plot steps plotted out versus frequency on the x-axis. So that's what we can do. We could say plot the upper bound axial and bending stress for this particular element versus a range of frequencies. And how you would go about doing that is you right click on the results folder down here and define a response graph. So the response graph, you can pick an individual node or you can pick a predefined location. If I had a sensor set up down here, I could set that up. But I'll just pick an individual node down here. For example, this should be if I set this to beams over here, I can pick one of these beam elements. This one here, for example, is element number 8835. It's the very bottom element here. So for that element, I could plot out frequency on the x-axis and one of these quantities on the y-axis: stress, displacement, velocity, acceleration. So I want to plot, for example, the stress on that element versus frequency on the x-axis for the full range of frequencies from basically 0 hertz up to 100 hertz, which was the maximum frequency for the harmonic applied force that we set up. Okay, and that gives me a stress plot for the stress on that element, number 8000, whatever, for a range of different frequencies. And you see we have one spike in the stress here at around about 1 point something hertz. We have another spike in the stress at around about 7.6 hertz, another spike in stress at around 22 hertz, another one at around 44 hertz, and another peak at around about 73 hertz roughly. Okay, and those correspond nicely to the natural frequencies that we found earlier in our frequency analysis. Okay. For the displacement at the top of the tower, then we could do the same thing. We could look at a displacement plot for a particular element, or we could look at the predefined location that's a workflow sensitive sensor I set up earlier on. Now, in order to use the sensor that I set up earlier on, I need to enable that in the results options. So under results options here, in the results options here, there's a lot of options we could go through at a future date, but the one we want to look at the moment is enabling sensors, or enabling use of the sensors to plot out our results graphs, rather, I suppose. So I'm going to just set that to all tracked data sensors, or I could individually pick out that sensor that I set up earlier on, but I'm going to just say all sensors. And now if I go to my results plots, I could plot out a response graph, same as for the bottom of the tower, and I could either pick out an individual node somewhere here, or I can pick from my predefined locations I have that sensor set up earlier on. Okay. Similar to what we did at the bottom of the tower, I'm going to plot a graph with frequency on the x-axis. Then on the y-axis I can pick stresses, I can pick displacements, all kinds of different displacements or rotations or moments or whatever it is. I'm just going to pick the resultant displacement, or the movement of the top of the tower on the y-axis, frequency on the x-axis, again for the full range of frequencies from 0 up to 100. And we get a similar enough plot to what we had previously. We get one massive peak in the response to the movement of the system at around the first natural frequency, slightly smaller peak at the second natural frequency, and it's kind of hard to see on this scale, but there would be a slight peak at the third natural frequency and fourth, and so on. Okay, so that's your response graph. We want one response graph for the movement of the top of the tower, and we've previously looked at the stress at the bottom of the tower. One thing I will point out maybe is that you can save these graphs either as an image file, but you can also save them as a comma-separated value file, effectively an Excel file. So you can open up your CSV file in Excel and you plot out the data points. I might just pause the video for a second and show you that. Okay, and just to demonstrate the comma-separated value data files, it basically spits out all the raw data, the results for this amplitude plot for those 89 different plot steps. I just want to plot these out just to kind of demonstrate how it groups the data points around about the natural frequencies. So I'm going to insert a scatter graph of those data points. And you'll see here the way it kind of clusters the simulation tests that it runs. It clusters them around about the first natural frequency, second, third, fourth, fifth, etc. Okay, so you see there are occasional simulations that are run in between those frequencies, but really it concentrates the simulation studies that it runs around about the natural frequencies. And that you can set that up in the simulation properties. So when we looked at the study properties earlier on, I didn't go into too much detail about it, but we set it to look at 10 natural frequencies, and when we went to advanced options, it concentrates where it places the study. So it does 8 data points per natural frequency in a bandwidth either side of that natural frequency, and it groups them. You can either set it to group them kind of spaced linearly or spaced logarithmically either side of those 10 natural frequencies. Okay, so I think that covers most of what we need to do there. Really setting up the study, setting up how many data points or how many studies it needs to run, one for each one of those data points, and then plotting out the response graphs for movement at the top of the tower and stress at the bottom of the tower. I've done it using beam elements. It gives reasonably good results. There are some slight inconsistencies, I suppose, in the stress at the bottom of the tower, probably to do with the beam elements more than anything. You could run it using solid elements, but it could take quite a while, depending on how dense the mesh is. It might take half an hour or an hour to run, and you may wind up with several gigabytes of data. So I think this, to demonstrate the principles that we want to look at with resonance and showing the different resonant peaks on the response graph, I think that's probably sufficient. Okay, so I'm going to stop the video. It's run on quite a bit longer than I had intended originally, but hopefully you should have enough information there to be able to replicate that study yourself. Okay, thanks for watching.